Tonight, when the sun goes down and the stars come out, I want you to do something. Pick one star, any star. That single point of light you're looking at, it's lying to you. Actually, that's not fair. The star isn't lying. But what you're seeing isn't what's actually there. That star might be showing you what it looked like when your great-great-grandmother was born, or when the Roman Empire fell, or when humans were still figuring out how to make fire. The night sky is not a photograph of the present moment. It's a mosaic of the past. Every single star is broadcasting from a different era in history, and by the time you finish this video, you will never be able to look at the stars the same way again. Let me show you what I mean. The speed of light is fast, like incomprehensibly fast, 299,792 kilometers per second. A beam of light could circle Earth 7.5 times before you finish reading this sentence. But here's the thing about space. It's so impossibly, absurdly, mind-breakingly vast that even light takes years to cross the gaps between stars. And this creates something genuinely wild. When you look at Sirius tonight, the brightest star in the sky, the light hitting your eyeball right now left that star 8.6 years ago. You're not seeing Sirius as it is, you're seeing Sirius as it was around 2017. That's just the closest one. Look at Vega, that bright bluish star overhead in summer. Its light departed around 2001, the year the first iPod came out. Arcturus, that brilliant orange beacon, 36.7 light years away. Its photons left around 1989 when the Berlin Wall was coming down. But it gets so much weirder. Polaris, the North Star, the one that guided every sailor and explorer for centuries, sits somewhere between 433 and 448 light years away. The light reaching your eyes tonight left during the reign of Queen Elizabeth I. Around 1578, Shakespeare hadn't written Hamlet yet. The telescope hadn't been invented, and the photons that would eventually hit your retina in 2026 were already on their way. Betelgeuse, that reddish star on Orion's shoulder, glows from approximately 650 light years away. Its light departed during the late Middle Ages. The Black Death was still a recent memory in Europe. And somewhere in Orion's vicinity, an ancient red supergiant was blasting light into the cosmos that wouldn't arrive on Earth until you were alive to see it. And then there's Deneb. Deneb is one of the most luminous stars visible to the naked eye, sitting somewhere between 1,500 and 2,600 light years away. Scientists actually aren't sure of the exact distance because the star is so bright it overwhelms the sensors on the Gaia satellite. If Deneb is at the higher estimate, the light you see tonight left around 600 BCE. Pythagoras was working out his theorem. The Buddha was teaching in India. And a blue supergiant star was firing photons into space that would take 26 centuries to reach your backyard. The farthest individual star most people can see without a telescope is RHO Cassiopeiae, a yellow hypergiant 550,000 times more luminous than the Sun. It sits roughly 8,200 light years away, its light left around 6,200 BCE, the Neolithic era. Humans hadn't invented writing yet, agriculture was just getting started, and the light you're seeing tonight is older than human civilization itself. So when you trace out a constellation like Orion, connecting the dots of the hunter's outline, you're not drawing a picture of something that exists in space. You're connecting points separated by over 1,000 years of history. Bellatrix on the right shoulder? About 250 light years, light from the 1770s. Alni Lam in the middle of the belt? About 1,344 light years, light from around 680 CE. You're literally drawing a line between the American Revolution and the early medieval period. The constellations are time machines, they just don't look like it. But here's where things get actually unsettling. Some of those stars you're looking at, they might not exist anymore. They could have exploded years or centuries ago, and the light from their destruction simply hasn't reached us yet. Betelgeuse is the most famous candidate. This red supergiant, about 15 to 20 times the mass of our Sun, is a confirmed future supernova. It will explode. The only question is when. In 2023, a study suggested Betelgeuse might be in late-stage carbon burning, a precursor phase to explosion that could mean centuries rather than millennia. Astronomers got excited, headlines got dramatic, But then NASA announced something in July 2025 that changed the conversation. Scientists discovered a companion star orbiting inside Betelgeuse's atmosphere. They named it Sawarha, and its presence helped explain some of Betelgeuse's weird brightness fluctuations that had been confusing astronomers for years. The new timeline? Probably hundreds of thousands of years before explosion. But here's the thing. Astrophysicist Ethan Siegel has calculated roughly a 1 in 4,000 chance that Betelgeuse has already exploded and we just haven't received the news yet. The light from the supernova could be racing toward Earth right now, and we'd have no idea until it arrived. If Betelgeuse does go supernova, whether tomorrow or in 10,000 years, the show would be spectacular. Neutrino detectors on Earth would fire hours before the visible light arrived, giving us an early warning. Then the star would brighten to roughly the luminosity of the full moon, concentrated into a single point, bright enough to cast shadows at night, visible in broad daylight for about a year. It would then fade over several years, leaving Orion permanently missing its left shoulder. At 650 light-years, it poses zero danger to Earth. The supernova danger zone is estimated at 50 to 100 light-years, and Betelgeuse is well outside that. But it would be the most spectacular astronomical event in recorded human history. For viewers in the southern hemisphere, there's an even more extreme candidate. Eta Carinae, sitting about 7,500 light-years away, is a binary system with a combined luminosity of 5 million suns and a primary star of roughly 100 to 120 solar masses. During its great eruption from 1837 to 1856, it became the second brightest star in the sky, despite being about 800 times farther away than Sirius. If it explodes as a hypernova, it could become the brightest supernova in recorded history, easily visible at noon. So the stars are showing us the past. Some might be dead already. But let's talk about something even stranger: their size. Our sun is big. Its diameter is about 1.4 million kilometers. You could line up 109 Earths across it. You could fit 1.3 million Earths inside it. It's a nuclear furnace, converting 700 million tons of hydrogen into helium every second, losing about 4 million metric tons per second as pure energy. But among stars, the sun is thoroughly average. Kind of small, actually. Betelgeuse has a radius of roughly 764 times our sun. If you dropped Betelgeuse where the sun is, its surface would extend past the orbits of Mercury, Venus, Earth, and Mars, reaching into the asteroid belt. You could fit approximately 700 million suns inside it. VY Canis Majoris is even bigger. At roughly 1,420 solar radii, it would engulf everything out past Jupiter's orbit. Light takes 6 hours to travel around its circumference. And here's the weird part. Its average density is 5 to 8 milligrams per cubic meter, over 100,000 times less dense than Earth's atmosphere. It's essentially a red-hot vacuum. The current record holder for largest known star is Stephenson 218, at roughly 2,150 solar radii. If it replaced the Sun, its surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Its volume is nearly 10 billion times the Sun's. Though its distance of about 19,000 light-years is uncertain by over 50%, so that record comes with some caveats. And then there's the other extreme. The smallest known main sequence star, EBLM J055557AB, has a radius of just 0.84 Jupiter radii. It's physically smaller than Jupiter despite being 85 times more massive. It represents the absolute minimum size for sustained hydrogen fusion. Any smaller and you don't get a star at all. But the real mindbreaker is neutron stars. These are the crushed cores of dead massive stars, packing 1.4 to 2.1 solar masses into a sphere just 20 kilometers across. About the size of a city, a teaspoon of neutron star material would weigh approximately 1 billion metric tons. That's roughly the mass of Mount Everest. In a teaspoon, The fastest spinning neutron star rotates 716 times per second. Let me give you a scale analogy that might actually help. If the Sun were a basketball, Earth would be a mustard seed about 26 meters away. Jupiter would be a golf ball at the 50-yard line of a football field. Betelgeuse would be a sphere 213 meters across, about 2 football fields wide. Stephenson 2 to 18 would be half a kilometer in diameter. And the nearest star, Proxima Centauri, another basketball, 4,400 miles away, the distance from Boston to Moscow. That's how empty space is. At Voyager 1's speed of 17.3 kilometers per second, the fastest any human-made object has traveled away from the Sun, reaching Proxima Centauri would take 73,000 years. Okay, so the stars are ancient light sources of incomprehensible size separated by impossible distances. But here's the part that genuinely changed how I see the universe. You're made of them, not metaphorically, not poetically, literally. Carl Sagan's famous line, "We are made of star stuff," is not a feel-good sentiment. It's a precisely accurate statement of astrophysics, confirmed by decades of nucleosynthesis research. Here's how it works. Stars are element factories. During their lifetimes, they fuse hydrogen into helium, then helium into carbon and oxygen. Massive stars continue the chain. Carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. Iron has the highest binding energy per nucleon. Fusing anything heavier absorbs energy rather than releasing it. That's why iron is the end of the line, and why massive stars die when their cores fill with it. The core collapses in less than a second, reaching temperatures over 100 billion degrees, and rebounds in a supernova that can briefly outshine an entire galaxy. The record holder, ASAS N15LH, peaked at 570 billion solar luminosities, 50 times brighter than the Milky Way, from a single star. The supernova's shock wave creates conditions extreme enough to forge elements heavier than iron through rapid neutron capture. But the heaviest elements, gold, platinum, and uranium, come primarily from an even more violent source, neutron-star mergers. In 2017, scientists detected gravitational waves from merger GW170817 and confirmed that a single collision produced gold equivalent to several times the mass of Earth, ejected at 10 to 30% the speed of light. Now here's the part about you. Over 90% of your body mass consists of elements forged inside stars. Only hydrogen, about 9.5% of your body mass, traces back to the Big Bang. Everything else came from stellar cores and stellar deaths. The oxygen you're breathing right now, about 65% of your body mass, was fused in massive stellar cores. The carbon forming the basis of every organic molecule in your body, about 18% of your mass, was created in the triple alpha process inside red giants. The calcium structuring your bones was synthesized during explosive silicon burning in a supernova. The iron in your hemoglobin, the molecule that makes blood red and carries oxygen through your body, was created in the final core collapse of a star that died billions of years before Earth existed. As Dr. Ashley King of the Natural History Museum puts it, it's very likely that there are a whole bunch of different stars that have contributed the elements we see in our own solar system. The atoms in your left hand may have come from a different star than the atoms in your right hand. Without stellar death, the universe would contain only hydrogen and helium. There would be no carbon, no oxygen, no iron, no silicon, no rocky planets, no water, no organic molecules, nothing remotely resembling life. You exist because stars died. Your body is stellar ash, rearranged by 4 billion years of evolution into a configuration that can look up at the night sky and wonder where it came from. Now you know. There's one more thing I want you to notice next time you're stargazing. The colors. Stars are not all white. They range from deep red to brilliant blue, and their color directly encodes their surface temperature. Blue means hot, red means cool, the exact opposite of how we label faucet handles. Orion offers the best naked eye demonstration. Betelgeuse on the upper left shoulder glows a distinct orange-red at about 3,500 Kelvin. Rigel at the lower right foot shines blue-white at about 12,100 Kelvin. The temperature difference between these two stars, visible simultaneously in the same constellation, is roughly 8,600 degrees. You can see it with your eyes if you know what to look for. But here's something weird about what you're seeing. 76% of all stars in the universe are red dwarfs, the coolest type at 2,400 to 3,700 Kelvin. Not a single one is visible to the naked eye because they're too dim. The stars you can see represent about 0.000001% of our galaxy, wildly skewed toward rare luminous giants. You're looking at the outliers, not the normal population. And a lot of what you're seeing isn't even what you think it is. That faint fuzzy smudge in Andromeda? That's not a star, that's the Andromeda Galaxy, containing roughly 1 trillion stars, sitting 2.5 million light years away. When its light began traveling toward you, the first Homo habilis were figuring out stone tools. It's the most distant object visible to the unaided human eye. The middle star in Orion's sword? Not a star. It's the Orion Nebula, a stellar nursery 1,350 light-years away and 24 light-years across, where thousands of new stars are actively being born, and approximately 50% or more of all stars exist in binary or multiple systems. Castor in Gemini appears as a single point of light, but is actually a sextuple system, 6 stars orbiting each other. The Mizar-Alcor pair in the Big Dipper's handle contains at least 6 stars total. Even planets hide among the stars. But you can learn to spot them. Planets shine with a steady light because they appear as tiny disks, rather than dimensionless points, so atmospheric turbulence averages out across their surface. Stars twinkle, planets do not. Let's talk numbers for a moment, because the scale of what you're looking at is genuinely incomprehensible. The observable universe contains an estimated 200 sextillion stars. That's a 2 followed by 23 zeros. Counting them at 1 per second would take over 6 trillion years, about 450 times the current age of the universe. This likely exceeds the number of grains of sand on all of Earth's beaches, though if you include all sand everywhere, deserts and ocean floors, sand probably wins. A more visceral comparison, 10 drops of water contain roughly the same number of H2O molecules as there are stars in the observable universe. The Milky Way alone holds 100 to 400 billion stars, yet on the darkest, clearest night, your eyes can see approximately 2,500 of them at once, about 0.000001% of our galaxy. From a light-polluted city, you might see a few hundred. An estimated 80% of Americans and 1/3 of all humanity can no longer see the Milky Way at all due to artificial lighting. A child born where 250 stars were visible will see only about 100 by age 18 as light pollution increases at roughly 9.6% per year. Across the observable universe, roughly 4,800 new stars ignite per second. In our galaxy alone, about 6 to 7 new stars form per year. Our sun has about 5 billion years left before things get interesting. When it exhausts its hydrogen fuel, its core will contract and heat up. Hydrogen fusion will migrate to a shell around the core, and the outer layers will begin to expand. The sun will swell into a red giant, eventually reaching roughly 256 times its current diameter, a radius of about 1.2 astronomical units, extending past Earth's current orbit. Its surface temperature will drop to about 2,600 Kelvin, turning it a deep orange red, but its luminosity will spike to 2,700 times its current output. Mercury and Venus will definitely be consumed. Earth's fate is genuinely uncertain. The sun will lose 33 to 38% of its mass, causing Earth's orbit to expand outward. But most recent models suggest the expanding solar atmosphere will probably still engulf our planet. As NASA puts it, I am confident that the sun will swallow Mercury and Venus, and not Mars. But the fate of the Earth, which resides in between, is less clear. After the red giant phase, the sun will shed its outer layers over roughly 75,000 years, creating an expanding, glowing planetary nebula. What remains will be a white dwarf, Earth-sized but containing half the sun's original mass, with an initial surface temperature exceeding 100,000 degrees Celsius. It will slowly cool over billions of years. Eventually, the carbon-oxygen core will crystallize into what is essentially a cosmic diamond. Astronomers have estimated such crystallized cores at roughly 6 billion trillion carats. After perhaps 10 trillion to 1 quadrillion years, it will cool into a theoretical black dwarf. But the universe is only 13.8 billion years old. No black dwarfs exist yet anywhere in the cosmos. The universe is too young. One final thing I want you to understand. The sky you see tonight is not the sky your ancestors saw, and it's not the sky your distant descendants will see. Stars have proper motion. They move relative to each other. Over tens of thousands of years, constellations deform and dissolve. The Big Dipper was unrecognizable 100,000 years ago and will look more like a shoe than a ladle 100,000 years from now. Polaris was not always the North Star. Earth's axis precesses over a 26,000-year cycle. Around 3000 BCE, the Egyptians used Thuban and Draco as their pole star. During the Roman Empire, there was no conspicuous North Star at all. Polaris will reach its closest approach to true north around 2100 AD, within about half a degree, then gradually cede the role. By around 14,000 AD, Vega will be the approximate pole star. 8 supernovae have been documented in the Milky Way throughout recorded history. The most famous, SN 10554, was recorded by Chinese astronomers as a guest star, visible in daylight for 23 days and at night for nearly 2 years. Its remnant is the Crab Nebula. The last Milky Way supernova visible to the naked eye was Kepler's supernova in 1604, over 4 centuries ago. We're statistically overdue. And the grandest future event? The Andromeda Galaxy is approaching us at 110 kilometers per second, traditionally expected to collide with the Milky Way in about 4 to 4.5 billion years. Though a 2025 study in Nature Astronomy found enough uncertainty that there's roughly 50% chance of no collision in the next 10 billion years. If it does happen, the two galaxies will merge over billions of years. Though individual star collisions would be virtually impossible since the average distance between stars is so vast. On the longest timescales, the universe's stelliferous era, the age of stars, will end. The longest-lived red dwarfs can burn hydrogen for up to 10 trillion years, but eventually all gas will be consumed. Star formation will cease entirely by about 10 to the 14 power years from now. The last stars will flicker out, and the universe will enter an era of cooling white dwarfs, neutron stars, and black holes. The final supermassive black holes will evaporate via Hawking radiation around 10 to the 100 power years. After that, only diffuse subatomic particles, photons, and neutrinos, drifting through an incomprehensibly vast, dark, cold emptiness. The next time you look up at the night sky, I want you to remember what you're actually seeing: a mosaic of moments from across time, stars broadcasting from different eras of human history, constellations that are tricks of perspective, connecting objects separated by centuries of light travel, ancient nuclear furnaces that forged every heavy atom in your body. You're not just observing the cosmos, you are the cosmos observing itself, assembled from the debris of ancient stellar explosions. Over 90% of your mass is stellar ash. The iron in your blood came from a supernova. The gold in any jewelry you own came from colliding neutron stars. Every breath you take contains oxygen fused in the core of a massive star before our solar system existed. The sky feels permanent, but it's not. Constellations shift, pole stars rotate, stars are born and die. And eventually, on timescales that dwarf human comprehension, every star now burning will go dark. But for this brief, extraordinary window, roughly 2,500 ancient nuclear furnaces are visible to your unaided eyes on any clear night. Each one tells a story written in light, arriving after a journey of years or millennia. The only equipment you need is darkness, patience, and the knowledge of what you're actually seeing. If this changed how you see the stars, subscribe. I make videos about the universe that will make you question everything you thought you knew. And next time someone asks why you're staring at the sky, you can tell them you're watching a 2.5 million-year-old movie playing out in real time.